Let's imagine you and your coworkers are designing a game for an arcade and want to add a high score table. You need the machine to display all of the players' scores from highest to lowest. You expect dozens of new people to play your game every day, and you need the table to be generated quickly. One of your coworkers suggests shuffling the scores randomly until they are all sorted. They call their algorithm permutation sort. Another suggests starting with a second blank list and moving each score as far down the list as you can until the score is greater than the one before it. They call this insertion sort. A third coworker claims one of the fastest sorting algorithms is called merge sort, which involves recursively splitting the list into smaller lists and merging them back together to form a full sorted list. And you, being the savvy computer scientist that you are, decide to compare these three ideas using big O notation. The goal of big O notation is to indicate, very roughly, how fast an algorithm's complexity will grow as the size of the input increases. As an example, let's find the big O of insertion sort. Let's say the list we are giving insertion sort has a length of n. For the first item, we can simply toss it into the empty list, which should take about one step. For the second item, we need to compare it to the first item and then insert it, which takes 2 steps. For the third item, we need to compare it to at most 2 other items, and so forth. Therefore, the number of steps that the algorithm takes is at most the sum of the integers between 1 and n. Since the sum grows quadratically as n increases, we can say that insertion sort is big O of n squared. Remember, we only want a rough idea of how fast the number of steps grows, which is why we never include coefficients or smaller terms in big O notation. All algorithms that grow quadratically are big O of n squared. Using similar reasoning, we can find the big O of the other 2 algorithms. Permutation sort is big O of n times n factorial, which is very bad, and merge sort is big O of n times log of n, which is very good. Since n times log of n grows the slowest, your team decides to implement merge sort into your arcade game, allowing users' scores to load quickly and efficiently.